Assalamualaikum warahmatullahi taala wabarakatuh. My name is Luna Dirmenta Abdul Razak, and today I'm going to present about my final year project, which is Magnetohydrodynamicflow plus 2 circular cylinder in staggered arrangement. So MHD comprised of the study on electrically conducting fluid and also the magnetic properties. And the motivation of this project is since the nuclear fusion can be the perfect sources of energy, so it begins when the two hydrogen isotope is combined, which is the deuterium and tritium, in order to produce the helium and neutron. So at high temperature, the superheated plasma is formed, and then the superheated plasma is confined by the strong magnetic field. From this diagram, we can simply understand that at high temperature, the superheated plasma is formed, and superheated plasma transformed to heat energy, and heat is absorbed by the blanket and transferred to the heat exchanger by the coolant. And from the heat exchanger, it can generate the electric current. So, but the problem here is at the heat exchanger, where due to the strong magnetic field, it will affect the flow in the heat exchanger to be steady. So it is the biggest facilities fusion reactor that is known as jet, but jet cannot be used for the certain area. And then the structure and the design of the jet is used for the ether, which is the ether aim is to fuse the atom to be together at high temperature, which is 10 times hotter than the sun. So the problem statement of this project is the first one is the two hydrogen isotopes which are combined together, and at high temperature the superheated plasma is formed, and the superheated plasma is confined by the strong magnetic field, which will affect the structure in the heat exchanger, and then the induced current in the fluid interact with the magnetic field, then it will produce the Lorentz forces. The Lorentz forces is actually can change the pattern of the flow, and the flow structure becomes steady. And when the flow structure becomes steady, the heat efficiency become decreased, thus the pressure drop increase. So in order to increase the heat transfer efficiency, so we have to transform the steady flow to be unsteady flow. That's why for my project, I'm going to study about the flow past two circular cylinder in staggered arrangement. When the steady flow past the cylinder, it will be unsteady flow. And then the objective of this project is the first one, to study the effect of the Hartmann number and high differences about the unsteadiness of flow on heat transfer efficiency. The second one is to study, to understand how the change of size for upstream cylinder can affect the structure of the flow. And the third one is to investigate the effect of the parameter to the pressure drop and the pumping power. So this is the research question. Next one is the literature review, where the first one is the effect MHD on the cooling blanket by the Ben Hadid showed that the magnetic field stabilized the flow, where the flow becomes steady. The second one is the relation to the Reynolds number from Qian and Peng, where the flow becomes steady at the low Reynolds number and become chaotic as increasing of the Reynolds number. Number 3 is the Hartmann number, whose sum show that the pressure loss depends on the Hartmann number. It can be simply said that when the Hartmann number is increased, the pressure loss also increase. And then the flow past the multiple cylinder from Verma and Gavardin, where when the multiple cylinder is arranged, there was a very change in the characteristic of the fluid structure, because this is due to the interference effect between the cylinder. So in this study, I'm going to study about the flow past the two cylinder, because the flow past two cylinder can provide the better understanding about the vortex dynamic. Number 5 is the effect on the heat efficiency from Talmage, concluded that the heat transfer can be improved by having the turbulence or unsteady flow. So in order to increase the heat efficiency, we have to convert the steady flow to be unsteady flow. And then the next one is the effect on the pressure drop by Matsuzaki, Umeda, and Takashi have the same opinion, where the amount of the pressure drop really depends on the Hartmann number. So the stronger the magnetic field, it will make the heat efficiency decrease, thus the pressure drop will be increased. And then number 7 is the flow past black body. This just like the other opinion about the other black bodies, where the Virasamy study about the cylinder that has been arranged three cylinder that has been arranged by side, where there were a gap flow were unstable and constantly reorienting, which had the effect of restructuring the wake flow. This can also be related with the interference effect just now when the multiple cylinder is added. And then the number 7 is the Zakharov-Kovic, where in the case of the square section, where the rectangular cylinder in the case of the square section is the prime example of sharp-edged bluff bodies, where the result is the separation location is fixed at sharp edge. Sharp edge bluff bodies does not actually depends on the Reynolds number. So number 8 is the two cylinder in staggered arrangement. Mehta and Kumar said that the staggered arrangement generally provide higher pressure drop and also higher heat transfer coefficient than inline arrangement. So the last one is the relation to the size cylinder, where banked it can satisfy the last objective just now, where the gap ratio and the diameter ratio between the two cylinders can also have the important effect on the voltage shading, where that's why for this study I'm also want to study about the flow past two cylinder, which the two cylinder has the different diameter. So we're gonna study about the how the two cylinder with different diameter can affect the flow structure and also the heat transfer. This is my flow plan where the computational fluid dynamics was set up, and then the validation was done regarding to the previous paper. And then we will run the simulation using the open form with the parameters such as the height and length of the channel, the inlet velocity, and also the Reynolds number. And then the manipulated variable, which is the variable that can be changed in this case, is the height differential and also the size of the upstream cylinder, in order to obtain the structure of the flow, the effect of the heat efficiency, and also effect of the pressure drop. First, the methodology. We begin with the governing equation, where the equation related to my cases, where my cases is the incompressible laminar flow 2D model. The first equation is the incompressible laminar unsteady Navier fluid equation, where Re is the Reynolds number equal to U max D over V, where U max is the inlet maximum inlet velocity, the D is the diameter of the cylinder, and V is the kinematic viscosity. Number 2 is the lift coefficient and drag coefficient, where F equal to lift force and drag force. Number 3 is the Strohan number, where F equal to period of vortex shading. Equation number 4 is for the magnetohydrodynamic as magnitude equation for the 2D model, where H is the friction term representing the Laurent forces effect on the flow. Number 5 is the energy equation, where T equal to temperature and PR is the Prandtl number. And the last one is the Prandtl number, where Cp equal to specific heat, K is the thermal conductivity, and mu is the dynamic viscosity. The first method is setting up the parameter, which is the parameter is the first one is diameter and radius of the cylinder, the height and length of the channel, the height differential, the blockage ratio, and the gap length. Number 2 is the geometry design. We design the geometry referring to the parameter just now, and we have the boundary condition for these cases. The boundary condition that should be considered in these cases is the first one, no slip condition, which is the at the top and bottom wall. And then number 2 is the average inlet velocity, which in order to get the average inlet velocity, we have to calculate using the formula 2 over 3 times inlet maximum inlet velocity. Number 3 is the kinematic viscosity, which is related to the Reynolds number. And then method number 3 is meshing. We do the meshing using the software Gmesh. And number 4 is simulation software. In simulation, we use the OpenFOAM software, and the output will be displayed in the ParaView. This is the validation for my project, which is the flow past single cylinder, and this is the geometry design, also the meshing with the given parameter. And this is the expected and also the present result at 200 Reynolds number for the pressure profile, and this is the also the expected result and the present result for velocity profile at 200 Reynolds number, and the graph and the result is still in progress. My Gantt chart for my FYP2 regarding what I'm gonna do with my FYP2. So that's all from me. Thank you.